You were taught that the sun is an ordinary star, and that is true. You were taught that the Milky Way is a spiral galaxy containing somewhere between 200 and 400 billion stars, and that is also true. You were taught that we orbit the sun and the sun orbits the center of the galaxy. Also true. But there is something that almost no school curriculum, almost no introductory textbook, almost no casual conversation about astronomy ever explains in a way that makes you feel its full weight. And when I say full weight, I mean that literally. There is something at the center of our galaxy, hidden behind enormous clouds of gas and interstellar dust, invisible to ordinary light, that is not a star, not a cluster of stars, not a nebula, not anything that the astronomers of previous centuries had any category for. It is an object that weighs 4 million times more than our sun, compressed into a region of space smaller than our solar system, so gravitationally extreme that not even light can escape from within its boundary. It is called Sagittarius A star, pronounced Sagittarius A star, and it is 26,000 light years from where you are sitting, a distance so immense that the light entering your eye right now, from whatever screen you are watching this on, has traveled for longer than that since the light that will eventually let us photograph this object was emitted. The story of how we found it, of how we tracked it, measured it, photographed it, and came to understand what it is also the story of something else. It is the story of how long it takes science to accept an idea that seems, at first, too extreme to be true. Of how many times the person who turned out to be correct was ignored, marginalized, or simply died before anyone agreed. Of what it actually looks like when human beings press against the boundary of the knowable. And it is the story of your own existence, because every atom in your body orbits this object, has always orbited it, will orbit it for billions of years after you are gone. But to understand what Sagittarius A is and why it took us so long to accept it, we have to go back to the moment the idea was first born. Not in a laboratory, not in a university, in a rectory in Yorkshire by candlelight in 1783. The year is 1783. The place is Thornhill in the West Riding of Yorkshire, England. A man named John Mitchell is writing a letter to the Royal Society of London, and in that letter, he is describing something that no human being has ever seriously considered before. Mitchell is not a full-time astronomer. He is a rector of the Church of England, a geologist, a natural philosopher, what the 18th century called a person of wide scientific curiosity. He has already made important contributions to geology and the theory of earthquakes. He is responsible for the first systematic attempt to measure the distance to the stars using what we now call statistical parallax. He has designed and built the apparatus that Henry Cavendish will use after Mitchell's death to measure the gravitational constant and calculate the mass of the Earth. Mitchell is, in short, one of those figures who did extraordinary work and is almost entirely unknown because none of his major contributions carried his name into posterity. But what he is writing in this letter is his most radical idea, and it begins with a deceptively simple question. If gravity can decelerate a cannonball, can it decelerate light? In the 18th century, the corpuscular theory of light, the idea that light is composed of particles, was dominant, championed by Newton himself. If light consists of particles, those particles must have mass, and if they have mass, gravity should act on them. An object thrown upward loses speed as it fights Earth's gravitational pull. Given enough gravity, a projectile could be launched and still fall back, unable to escape. So Mitchell asked, what if the same applied to light? The mathematics was not complicated, given the Newtonian framework of the time. For a sphere of given mass and density, there would be a radius at which the escape velocity equaled the speed of light. Any object smaller than that radius, or any object of that mass compressed to that radius, would prevent light from escaping. The surface would launch light, which would decelerate, slow to a stop, and fall back. The object would be there, It would have mass, it would exert gravity on everything around it, but it would be invisible, perfectly dark, detectable, if at all, only by its gravitational effect on surrounding matter. Michel called these objects dark stars. His letter estimated that a dark star would need to be about 500 times the radius of the Sun at solar density, an object so massive that it strained imagination. He sent his calculations to the Royal Society. Henry Cavendish read them. They circulated, briefly, in the small world of natural philosophy. And then they were forgotten. Not because they were wrong, exactly, though Mitchell's Newtonian framework was incomplete in ways that would only become clear a century later, but because there was nothing to do with the idea. No instrument existed that could detect a dark star. No mathematical framework existed to explore the idea's deeper implications. And there is something deeply human about what happened next. The idea sat, dormant, for nearly a century, until a French mathematician named Pierre-Simon Laplace independently derived the same conclusion in 1796, published it in 2 editions of his Exposition du Système du Monde, and then quietly removed it from the 3rd edition because he had become convinced that the wave theory of light, which was gaining strength, made the concept of a dark star incoherent. Waves, unlike particles, might not be subject to gravity. Michel died in 1793. Laplace's retraction buried the dark star concept for another 100 years. 2 men, working independently, had arrived at one of the most profound ideas in the history of physics, and the world was not ready for either of them. There is a pattern here I want to name explicitly because it will repeat throughout this story with a regularity that is almost painful to watch. The pattern is this. A correct idea arrives before the tools exist to test it, before the mathematics exists to fully explore it, before the cultural moment exists to receive it. The person who has the idea is sometimes ignored during their lifetime. Sometimes they are acknowledged, only to be quietly erased later. Sometimes they die, never knowing whether they were right. And the field moves on, reinventing the idea from scratch a generation or a century later, giving credit to the reinventor rather than the originator. This is not a conspiracy. It is something more mundane and more difficult to fix. It is the ordinary behavior of human institutions confronted with the extraordinary. Mitchell's dark star was the right idea in the wrong century. The mathematics to take it seriously would not exist for another 100 years, and it would arrive not from an observatory, but from a patent office in Bern, Switzerland. The year is 1905. Albert Einstein is 26 years old. He holds no academic position. He has a job as a technical expert, 3rd class, at the Swiss Federal Patent Office in Bern. He examines patent applications and decides whether they are novel and useful. He does this 6 days a week. In his remaining hours, he does physics. And in 1905, a year that historians of science would later call the Annus Mirabilis, the miracle year, Einstein publishes 4 papers. The first explains the photoelectric effect, for which he will eventually receive the Nobel Prize. The second explains Brownian motion, providing the most direct evidence yet for the reality of atoms. The third introduces the special theory of relativity, which fundamentally revises our understanding of space and time. The fourth derives the most famous equation in the history of science, E equals mc squared. Any single one of these papers would have established a major scientific reputation. Together, they transform physics. But special relativity is not yet the whole story. Special relativity describes how space and time behave in the absence of gravity. It takes Einstein 10 more years, years of extraordinary difficulty, false starts, collaboration and conflict with mathematicians, moments of deep discouragement, to arrive at what he will call the general theory of relativity. General relativity, published in 1915, is a fundamentally different description of gravity from what Newton had given the world 2.5 centuries earlier. Newton described gravity as a force, a mysterious, instantaneous pull between masses across empty space. Einstein describes it as something else entirely. Mass and energy, he says, curve the fabric of spacetime, the four-dimensional continuum in which all events occur. And what we experience as gravity is not a force at all. It is the curvature of spacetime, telling matter and energy how to move. The analogy of a rubber sheet distorted by a heavy ball captures something of the idea, but it is misleading in one crucial respect. It shows a two-dimensional surface being curved by a third dimension we can see. Real spacetime curvature is four-dimensional, and we are embedded in it. We cannot step outside it to see the curve. We can only feel its effects, which we experience as gravity. Einstein's field equations, a set of 10 coupled, nonlinear partial differential equations, describe precisely how matter and energy curve spacetime and how that curvature affects the movement of matter and energy. They are extraordinarily complex. Einstein himself, when he published them, was not certain that an exact solution would ever be found. He was wrong about that, within weeks. Karl Schwarzschild is a German physicist and astronomer, born in Frankfurt in 1873. By 1915, he is the director of the Astrophysical Observatory in Potsdam and one of the most respected astronomers in Germany. He is 52 years old, well past the age at which most physicists do their best work, and he is serving as an artillery officer on the Eastern Front of the First World War. Schwarzschild had volunteered for military service. He is at the Russian front, calculating artillery trajectories, sleeping in trenches, and in the small hours between military duties, doing physics. He obtains a copy of Einstein's field equations shortly after they are published. He reads them in the trenches, and he finds a solution. The Schwarzschild solution describes the space-time geometry outside a perfectly spherical, non-rotating, electrically neutral mass. It is the simplest, non-trivial solution to Einstein's equations, and it is exact. And embedded within it, Schwarzschild finds something that even he seems not to have fully grasped. For any mass, there is a critical radius, now called the Schwarzschild radius, below which, if all the mass were compressed, the escape velocity at the surface would exactly equal the speed of light. At smaller radii, the escape velocity exceeds the speed of light. Nothing could escape. The equations become singular at this boundary. For the Sun, the Schwarzschild radius is approximately 3 kilometers. For the Earth, it is 9 millimeters. For a human being, it is on the order of 10 to the minus 25 meters, smaller than a proton by many orders of magnitude. These numbers are so far removed from any physical object we know that the singularity in Schwarzschild's equations seemed, to most physicists, to be a mathematical curiosity rather than a description of anything real. Schwarzschild wrote to Einstein with his solution. His letter included a line of almost touching modesty. He wrote that the war had been kind enough to allow him time for this excursion into your land of ideas. Einstein was astounded. He read the paper to the Prussian Academy. He published it on Schwarzschild's behalf. Karl Schwarzschild never returned from the Eastern Front. He had contracted pemphigus, a painful autoimmune skin disease, possibly from exposure to chemical weapons or harsh conditions. He was invalided home in March 1916. He died on May 11, 1916. He was 42 years old. In the months between solving Einstein's equations in the trenches and his death, Schwarzschild also found the interior solution, describing the geometry inside a sphere of incompressible fluid, and published a second paper. He was working at extraordinary speed, possibly aware that he was dying. He never knew what his equations truly described. The concept of a black hole, of what actually happens at the Schwarzschild radius, would not be worked out for another half-century. But the mathematics was his. The singularity was his. The Schwarzschild radius bears his name, as it should. For the next 30 years, the physics community argued over whether the Schwarzschild singularity was physically real or merely a coordinate artifact, a glitch in the way the equations were written rather than a feature of actual spacetime. The predominant view, including Einstein's own, was that nature would somehow prevent the singularity from forming. A real object made of real matter could not collapse to a point. Something would stop it.
Einstein spent the years after 1916 actively resisting the conclusions embedded in his own equations. In 1939, the same year Oppenheimer would publish his collapse paper, Einstein published a paper arguing that the Schwarzschild singularity could not be formed in practice. His argument was that the matter composing a collapsing star would stabilize before reaching the critical radius. He used an idealized model of a rotating disk of test particles to make this argument. The model had unrealistic assumptions. The conclusion was wrong. But Einstein was Einstein, and the paper was published in the Annals of Mathematics, and its authority delayed serious investigation for years. What makes this story so instructive is not Einstein's error. Brilliant people make errors, and a single wrong paper does not diminish a life's work of extraordinary achievement. What makes it instructive is the mechanism by which the error slowed the field. When the most celebrated physicist in the world says something cannot exist, other physicists do not rush to prove him wrong. They tend to assume there is wisdom in his position they have not yet grasped. They spend energy accommodating his conclusion rather than testing it. The sociology of science is not immune to hierarchy and authority, no matter how earnestly it aspires to evidence alone.
The correct understanding of what happens at the Schwarzschild radius came slowly through the work of mathematicians and relativists in the 1950s and 1960s, who developed new coordinate systems that made the behavior of spacetime at the horizon transparent. In Schwarzschild's original coordinate system, the equations appeared to blow up at the horizon, giving the false impression that something physically singular was happening there. In better chosen coordinates, it became clear that the horizon is not a place of infinite anything from the perspective of an infalling observer. It is a point of no return, a one-way membrane. But locally, the physics there is unremarkable. An astronaut crossing the event horizon would not feel a sudden catastrophic force. They would cross a smooth, uncollapsed region of spacetime. They would simply be unable, thereafter, to send any signal back. That view would persist until 1939, and what changed it was a paper published on September 1st, 1939, the day Germany invaded Poland and the Second World War began, a paper that, for that reason, was barely noticed at all. Schwarzschild had given physics the equations, but equations are not proof. The question that remained, the one that would haunt the field for decades, was whether any of this could actually happen to a real star made of real matter in a real universe. J. Robert Oppenheimer is, by 1939, one of the most brilliant theoretical physicists in the United States. Born in New York City in 1904 to a wealthy German Jewish family, he studied at Harvard, then Göttingen in Germany, then Cambridge, absorbing quantum mechanics directly from the founders of the field, Niels Bohr, Max Born, Paul Dirac. He returned to America in 1929 and built, at Berkeley and Caltech, one of the most celebrated theoretical physics groups in the country. Oppenheimer had an intellect of startling breadth. He read Sanskrit for pleasure. He could quote Dante in the original. His graduate seminars attracted students from across the country, drawn not only by the physics, but by the quality of his attention, the sense that he was fully present, genuinely interested, that the problem on the chalkboard was the most important thing in the world at that moment. His students revered him. In 1939, Oppenheimer turned his attention to neutron stars, extremely compact, dense objects that had recently been proposed as the remnants left behind after certain types of stellar explosion. He and his graduate student George Volkoff established the maximum mass a neutron star could have before gravity overwhelmed even the quantum mechanical pressure that had been holding it up. This limit, now called the Tolman-Oppenheimer-Volkoff limit, is approximately 2 to 3 times the mass of the Sun. The question then arose, what happens to the core of a star more massive than this limit when it exhausts its fuel and collapses? What holds it up? The answer, Oppenheimer and his student Hartland Snyder showed in their September 1939 paper, was nothing. A sufficiently massive stellar core, collapsing under its own gravity, would continue to collapse. The quantum pressure of neutrons, the last resort, would be overwhelmed. The core would pass through what we now call the event horizon, the point of no return, the Schwarzschild radius, and keep going. From the perspective of a distant observer, the collapse would appear to slow and freeze as the collapsing surface approached the event horizon, becoming more and more redshifted, fading. But from the perspective of the collapsing matter itself, the horizon would be crossed and the collapse would continue. The paper was careful and precise. It used full general relativistic equations. It showed the results clearly. And it was published on September 1st, 1939, the day that Germany invaded Poland and the world lurched into the largest conflict in human history.
The physics community had other things to think about. The paper was read by very few people. Those who did read it largely regarded the conclusion, indefinite gravitational collapse, a space-time singularity, as an artifact of the idealized model. Real matter could not do this. Real stars would not collapse so cleanly. Some form of rotation or asymmetry or unknown physics would intervene. This objection was not unreasonable, but it was wrong. And it would take until 1965, 26 years, for Roger Penrose to prove, rigorously and generally, that gravitational collapse to a singularity is not an artifact of symmetry. It is a generic outcome of general relativity. Any object that collapses within its Schwarzschild radius forms a singularity. There is no escape. Oppenheimer did not pursue the implications of his 1939 paper. The war came. Los Alamos came. The Manhattan Project came. The bomb came. And then the post-war world, with its anxieties and politics, consumed him in ways that physics did not survive. He was stripped of his security clearance in 1954, an act of institutional brutality whose motivations were partly political and partly personal, and which ended his active role in physics.
He died in 1967. He never returned to the problem of what happens to collapsing stars. Whether he remained interested, or whether the weight of everything that followed Los Alamos had simply extinguished that curiosity, is not recorded with certainty. What is recorded is that he was right. He was right in 1939, and the concept he described, the complete gravitational collapse of a stellar remnant past all possibility of stopping, was the thing that John Wheeler, in 1967, would name with two words that would permanently change how humanity thinks about extreme objects in the universe.
Oppenheimer had shown the collapse was inevitable, but the thing he described had no name, and without a name, it remained, for most of the physics community, a mathematical abstraction rather than a physical object. That was about to change, in a lecture hall in New York, when someone in the audience shouted two words. John Archibald Wheeler is, in 1967, one of the preeminent theoretical physicists in the world, a student of Niels Bohr, a collaborator of Einstein, a man who has thought as deeply as anyone alive about what general relativity actually means, about what it implies for the structure of space-time, about the boundary between physics and philosophy that becomes blurry at the very small and the very dense. Wheeler understood something that physicists often underestimate, that language shapes thought, that the names we give to things influence how easily we can think about them, how naturally they fit into our conceptual landscape. For decades, the objects described by Oppenheimer and Snyder's equations had been called collapsed stars, or frozen stars, or Schwarzschild singularities. These names were accurate in various ways, but none of them conveyed the essential, visceral nature of the thing, an object from which nothing, not matter, not radiation, not information of any kind, could escape. Wheeler had been using the phrase gravitationally completely collapsed object in his lectures. Accurate, cumbersome, unmemorable. In December 1967, at a talk at the NASA Goddard Institute for Space Studies in New York, Wheeler was discussing these objects when, according to his own recollection, someone in the audience, a graduate student, unidentified, who presumably did not realize what they were doing, shouted out the term black hole. Wheeler loved it immediately. He used it in his next publication. He used it in every lecture and paper thereafter. And within a year, the term had spread through the physics community and into popular culture,
with the speed of a concept that had been waiting for exactly the right words. Black hole is a perfect piece of scientific nomenclature. It is immediate. It is visceral. It captures the essential physics. Black, because nothing comes out. Hole, because things fall in and cannot return, in 2 syllables. It is so good that it is now almost impossible to think about the concept without the words.
Wheeler was also a master science communicator and a profoundly generative thinker. He coined other terms that reshaped physics: quantum foam, wormhole, it from bit, the proposal that information is more fundamental than matter or energy. He supervised the PhD theses of Richard Feynman, Kip Thorne, and Hugh Everett III, among others. His influence on mid-20th century theoretical physics was enormous and pervasive in ways that do not reduce to any single discovery with his name on it. But in 1967, what Wheeler did not have was proof. He had mathematics that pointed unambiguously at the conclusion. He had Penrose's theorems. He had the Oppenheimer-Snyder paper. He had the entire machinery of general relativity, which no experiment had yet contradicted. But he had never seen a black hole. No one had. Because black holes, by definition, emit no light. A black hole in empty space is the closest thing to perfect invisibility that the laws of physics allow. To find one, you have to look not at the black hole itself, but at what it does to the space around it. And that required a completely different kind of observation.
Wheeler had given the object its name. But naming something is not the same as understanding it. And the deepest question about black holes, what happens to the information about everything that falls in, was about to be asked by a man who had been told he had 2 years to live.
Stephen Hawking is 21 years old when, in 1963, he is diagnosed with amyotrophic lateral sclerosis, motor neuron disease. The doctors give him approximately 2 years to live. He is in the middle of his doctoral studies. He has not yet done any work of significance. He is, by his own later account, not working very hard. He had coasted through Cambridge on raw ability and was coasting through his doctorate with something less than full commitment. The diagnosis changes that. Not immediately, and not in the way the inspirational version of the story usually tells it. First, there is profound depression. The feeling that there is no point in completing a PhD he will never use. But then, slowly, something else. The realization that there was a lot he wanted to do, and that the time to do it was not infinite. He stayed with physics. He married Jane Wilde, who would later write with both love and difficulty about the years that followed. He finished his doctorate on properties of expanding universes, and then he began to think about black holes.
The question Hawking was drawn to was one that most physicists had not bothered to ask, perhaps because the answer seemed obvious. What happens when you apply quantum mechanics to a black hole? General relativity describes the very large. Quantum mechanics describes the very small. Both are extraordinarily accurate theories within their respective domains, but they are fundamentally incompatible. The mathematical framework of one cannot be straightforwardly applied to the other. And a black hole, which is a product of general relativity, is also an object where quantum effects at the horizon might be significant. It sits precisely at the boundary between the 2 great theories. In quantum mechanics, the vacuum, what we call empty space, is not empty. At the quantum level, space seethes with what are called vacuum fluctuations, pairs of virtual particles and antiparticles that spontaneously appear from the quantum foam, exist for a time constrained by the uncertainty principle, and annihilate back into nothing. This happens everywhere, all the time, throughout the universe. It is not speculation. The effects of vacuum fluctuations are measurable, and they have been measured in phenomena like the Casimir effect and the Lamb shift in atomic spectra.
Now consider what happens at the event horizon of a black hole. A pair of virtual particles appears, one just outside the horizon, one just inside. In normal space, they would annihilate almost immediately. But the one inside the horizon cannot interact with the one outside. The horizon is a one-way membrane. The particle outside, now unable to find its partner to annihilate with, must become real. It must carry away energy.
From the perspective of a distant observer, it appears that the black hole has emitted a particle. That particle carries energy away from the black hole. By conservation of energy, the black hole must therefore lose a tiny amount of mass with each emission. Over time, astronomical timescales so vast they are almost beyond comprehension. A solar mass black hole would take 10 to the 67 years to evaporate, compared to the 13.8 billion year age of the universe. A black hole would lose all its mass. It would evaporate. Hawking published this result in 1974 in a paper titled Black Hole Explosions in the journal Nature. He was 32 years old. He had been told he had 2 years to live 11 years earlier.
The reaction was initially skeptical. Even among physicists who respected Hawking deeply, the conclusion seemed too radical. Black holes were defined as objects from which nothing escaped. Here was Hawking saying they radiated. The claim required accepting that quantum effects near the event horizon could be significant enough to produce real particles, a regime where both quantum mechanics and general relativity are relevant, and where our ability to calculate is limited precisely because we lack a theory that unifies them. But the calculation stood up. Other physicists checked it. They found different ways to derive the same result. The temperature of the radiation Hawking predicted, extraordinarily cold for any stellar mass or supermassive black hole, but theoretically non-zero, became known as the Hawking temperature. The radiation itself is called Hawking radiation. It has never been directly observed, because for any black hole we know of, the temperature is unimaginably lower than the cosmic microwave background. The universe is currently too warm for the signal to be detectable above the noise, but it is almost certainly real.
And it creates a problem that has occupied the greatest minds in physics for 50 years and which remains unsolved. If the black hole evaporates, then everything that ever fell into it, all the information about the state of every particle that crossed the event horizon, must eventually come out. Physics as we understand it does not permit information to be destroyed. Information can be scrambled, encrypted, made effectively inaccessible, but the laws of quantum mechanics demand that it not be annihilated. Hawking's original calculation, however, suggested that the radiation emitted was perfectly thermal, perfectly random, with no memory of what had fallen in. This is the black hole information paradox. If Hawking's calculation is right and the radiation carries no information, then information is destroyed when a black hole evaporates. This would violate one of the most fundamental principles of quantum mechanics.
Hawking believed for decades that information was destroyed. Other physicists, particularly string theorists, believed it must be preserved and encoded in the radiation in some subtle, scrambled way. The debate has gone on since 1974. New theoretical tools, holography, the ADS/CFT correspondence, the concept of quantum entanglement between Hawking radiation and the black hole interior, have brought physicists closer to a resolution, but a complete, satisfying answer still does not exist. Hawking died in 2018, on the 119th anniversary of Einstein's birth. He was 76 years old. He had survived his diagnosis by 55 years. In his final years, he had moved toward the position that information might be preserved, though he never fully committed to a mechanism that satisfied him. The information paradox remains the central unsolved problem at the boundary between quantum mechanics and general relativity. Its resolution, when it comes, will likely require the theory of quantum gravity that physics has been seeking for a century.
By the 1990s, the evidence for black holes had become extremely strong from multiple directions. X-ray binaries, systems in which a compact object stripped gas from a companion star, showed all the expected signatures. Active galactic nuclei, galaxies with extraordinarily luminous cores powered by matter falling into a central object, were best explained by accretion onto a supermassive black hole. The physics pointed consistently in one direction. But there is a difference between circumstantial evidence and direct evidence. The physics community knew what black holes should produce. It had not yet proven that a specific object in a specific location was unambiguously a black hole. The best candidate for such a proof lay at the center of our own galaxy. Astronomers had known since the 1970s that the galactic center harbored an intense, compact source of radio emission. They called it Sagittarius A star, Sgr A star for short, the asterisk denoting the intensity of the radio emission. It was at the dynamical center of the Milky Way. Something was there. But the galactic center is hidden from optical telescopes by a wall of gas and dust so thick that visible light cannot penetrate it. Looking toward the galactic center with an optical telescope is like trying to look through 10 magnitudes of extinction. You would need a telescope 100,000 times more sensitive just to see the light that gets through.
But infrared light, with its longer wavelength, can penetrate dust that blocks visible light. And by the late 1980s and early 1990s, improvements in infrared detectors and in the size of ground-based telescopes made it possible for the first time to begin imaging individual stars near the galactic center in the infrared. There was another obstacle: the atmosphere. Earth's atmosphere is turbulent. The columns of air at different temperatures that produce the shimmering heat haze on a summer road also blur the images of stars. A star that should appear as a point becomes a smeared blob. For nearby stars, this is merely annoying. For stars at the galactic center, 26,000 light-years away, where even the largest telescopes are trying to resolve objects separated by fractions of an arcsecond, atmospheric turbulence was catastrophic. The solution was a technology called adaptive optics. A bright star near the target field, or an artificial star created by firing a laser beam into the sodium layer of the upper atmosphere, serves as a reference point. The turbulence-induced distortion of this reference star is measured hundreds of times per second by a sensor. A computer calculates the correction needed. A deformable mirror, a mirror whose surface can be physically reshaped by hundreds of actuators, applies the correction in real time. The result? Images from a ground-based telescope that approach the diffraction limit, the theoretical maximum resolution set by the size of the mirror, as if the atmosphere were not there. Adaptive optics technology matured in the 1990s, and two teams, working independently and in competition, used it to begin the most painstaking astronomical surveillance campaign in history. The European team, based at the European Southern Observatory's Very Large Telescope in Chile and led by Reinhard Genzel of the Max Planck Institute for Extraterrestrial Physics, began their monitoring campaign in the early 1990s. The American team, based at the W.M. Keck Observatory on Mauna Kea in Hawaii and led by Andrea Ghez of UCLA, began shortly after. Both teams were doing the same thing, tracking individual stars in the region within a few light-years of Sagittarius A star, measuring their positions year after year, watching for movement. And movement is what they found. Stars near the galactic center were moving at extraordinary speeds, thousands of kilometers per second, on arcs that were unmistakably orbital. They were going around something.
The key star was one designated S2 by the European team, S02 by the American team. S2 traces a complete elliptical orbit around the central radio source in just 15.9 years, an eye blink by astronomical standards. Its closest approach to the center, called periapsis, brings it within about 17 light hours, just a bit farther than the distance from the Sun to Neptune. At periapsis, S2 moves at approximately 7,600 kilometers per second, about 2.5% of the speed of light. When you fit an orbit to these numbers, when you use the laws of Newtonian gravity, sufficient for stars still this far from the center, to determine what mass must be sitting at the focus of the ellipse, the answer is unambiguous. To explain S2's orbit, and the orbits of the dozens of other stars monitored by both teams, there must be an object at the center with a mass of approximately 4 million solar masses.
4 million times the mass of our Sun, within a region whose radius is smaller than our solar system. The density implied by those numbers, a mass of 4 million suns in a region smaller than Pluto's orbit, rules out every possible alternative explanation, except a black hole. A cluster of ordinary stars of that total mass would be far larger. A cluster of neutron stars would be unstable. They would merge. Dark matter at those densities would have observable effects it does not have. A black hole, a single object of 4 million solar masses, is the only thing that fits.
Both teams published landmark papers. Both teams continued monitoring over decades, tracking more stars, refining the mass measurement, mapping the precise location of the radio source at the center. The evidence accumulated to a level of certainty that is rare in observational astronomy. In October 2020, the Royal Swedish Academy of Sciences announced the Nobel Prize in Physics. Half was awarded to Roger Penrose for his 1965 mathematical proof that singularities are a generic outcome of general relativity. The other half was split between Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of the Milky Way.
There is something worth noting about Andrea Gez's position in this story. She entered astronomy at a time when women astronomers were not rare, but were rarely celebrated. She built the Galactic Center Group at UCLA. She competed fiercely with Genzel's European team, a competition that was scientifically productive for both teams, sharpening their methods and pushing their technology faster than either would have alone. She became the fourth woman in history to receive the Nobel Prize in Physics. And she did so for proving that at the center of our galaxy, there exists an object that Michel imagined in 1783, that Schwarzschild described mathematically while dying in a trench in 1916, that Oppenheimer showed was a physical inevitability in 1939, and that Wheeler named in 1967. But I want to stay with the science for a moment longer, because the stellar orbit data accumulated by both teams contains something extraordinary that is easy to gloss over. These astronomers were not merely confirming the existence of the black hole, they were measuring, in real time, the effects of extreme gravity on stellar dynamics. Some of the stars near the galactic center showed small but detectable deviations from simple Newtonian orbits, deviations that matched precisely the predictions of general relativity. The gravitational redshift of light from S2 was measured as it approached periapsis in 2018. The precession of S2's orbital ellipse, analogous to the famous precession of Mercury's orbit that was one of the first tests of general relativity, was detected. In each case, the data agreed with Einstein's equations.
We were using stars as test particles in the gravitational field of a 4 million solar mass black hole to test the theory of gravity. And the theory passed. At scales and intensities of gravity that Newton never imagined, in an environment that Schwarzschild never lived to understand, Einstein's field equations, written in 1915 in Berlin by a man who had never seen anything more extreme than the orbit of Mercury, continued to give the right answer.
Genzel and Ghez had proven the black hole existed beyond any reasonable doubt. The mass was measured, the location was pinned, but there was still something no human being had ever done: look at one directly. And to do that, someone had to build a telescope the size of the Earth.
Knowing that a supermassive black hole exists at the galactic center and actually seeing it are two very different things. Genzel and Ghez had proven the mass and location of Sagittarius A star through its gravitational influence on surrounding stars, but no one had ever seen the black hole itself, its event horizon, its shadow, the boundary where physics as we understand it terminates. In principle, a black hole must cast a shadow. Light from behind and around the black hole is bent by gravity. Some is captured, some is deflected into tight arcs, and some escapes. The region from which no light can escape appears dark against the bright, hot plasma swirling around the black hole. This dark region, the shadow, is actually somewhat larger than the event horizon itself, because gravity focuses light from behind the black hole toward us, creating a ring of concentrated emission around the central darkness. The innermost stable orbit of photons, the photon ring, appears brighter than the surrounding material, while the interior of this ring is dark.
The problem was resolution. Sagittarius A star has a mass of 4 million suns. Its event horizon has a radius of approximately 12 million kilometers. At a distance of 26,000 light-years, this subtends an angle of about 50 micro-arcseconds in the sky. To put that in perspective, it is roughly equivalent to being able to resolve an orange placed on the surface of the moon. No optical telescope, no matter how large, could achieve that resolution.
At optical wavelengths, diffraction limits the resolution of any single aperture to much larger scales. But radio telescopes work at millimeter and submillimeter wavelengths, and the resolution of an interferometric array, a network of telescopes that observe simultaneously and combine their signals, is determined not by any individual dish, but by the maximum separation between dishes. The larger the separation, the higher the resolution. If you could link radio telescopes on opposite sides of the Earth, you would have a virtual aperture the size of the planet. At millimeter wavelengths, the resolution of such an Earth-sized array would be sufficient, barely, to image the shadow of Sagittarius A star.
This is the concept behind the Event Horizon Telescope, or EHT. From the early 2000s onward, a global collaboration began the painstaking technical work of connecting telescopes on 6 continents, synchronizing their clocks to atomic precision using GPS and hydrogen masers, recording data on high-density hard drives at rates measured in gigabits per second, and arranging for all those hard drives to be physically shipped to processing centers at MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy. In April 2017, for a window of approximately 10 days, the array turned toward 2 targets simultaneously: Sagittarius A star and the supermassive black hole at the center of Messier 87, a giant elliptical galaxy 55 million light-years away, harboring a black hole 6.5 billion times the mass of our Sun. The data collection was the easy part. Petabytes of raw data had to be correlated, meaning the signals from each telescope had to be precisely aligned in time and combined, taking into account the different arrival times of signals from the same source at different locations on Earth, the different atmospheric conditions at each site, and the different characteristics of each telescope. The data analysis took nearly 2 years, and in April 2019, in a simultaneous press conference at 6 locations around the world, the EHT collaboration released the first image in human history of a black hole. It was the black hole in M87, a glowing, asymmetric ring of hot plasma, brighter in the south than the north, consistent with relativistic beaming from matter moving toward us, with a dark interior. The size and shape of the shadow matched the predictions of general relativity with extraordinary precision. The mass inferred from the shadow size was consistent with prior measurements from stellar dynamics.
The image was blurry by the standards of optical astronomy. The resolution of a planet-sized radio interferometer is still not comparable to what a space telescope can achieve at optical wavelengths. But it was real. It was the event horizon of a black hole. Not an artist's impression, not a computer simulation, not an indirect inference, a direct image. For Schwarzschild, dying in 1916, for Oppenheimer, writing his paper as the world went to war, for Wheeler, naming the thing in 1967, for Genzel and Ghez, tracking stars for decades, for every graduate student who spent nights at a telescope, every engineer who built the receivers, every programmer who wrote the correlation algorithms. This was the result.
M87 was the proof of concept, 55 million light-years away, a black hole 6 billion times the mass of our Sun. But it was never the real target. The real target was ours. And 3 years later, the collaboration turned the array back toward the center of the Milky Way. 3 years after M87 star, in May 2022, the Event Horizon Telescope collaboration released its second image, this time Sagittarius A star, the black hole at the center of our own galaxy. Imaging Sagittarius A star was actually harder than imaging M87 star, despite the fact that Sagittarius A star is far closer. The reason is that Sagittarius A star is much less massive, and therefore much smaller. Its event horizon is crossed far more quickly by orbiting plasma. Where the plasma orbit around M87 star takes days to weeks, the plasma orbit around Sagittarius A star takes minutes. The image was not stable. It flickered and changed on timescales of the observing run itself, as if the subject kept moving. The collaboration had to develop new analysis techniques to average across this variability and produce a coherent image. The result was an image that matched the general relativistic prediction, a bright ring slightly asymmetric, surrounding a dark central region. The shadow size corresponded to a mass of approximately 4 million solar masses, consistent, to within measurement uncertainty, with everything Genzel and Ghez had measured over 30 years of stellar orbit tracking.
Einstein's equations, written in 1915, had passed another test. Applied to an object 26,000 light-years away, composed of matter in conditions of extreme density and gravity, those equations remained accurate. The universe is described by the same laws in the most extreme environments we can find as in the mundane physics of everyday life. And there is something almost no commentary on this image mentions. The light captured by the EHT, the photons that formed the image, left the vicinity of Sagittarius A star 26,000 years ago. When that light was emitted, the Toba volcanic supereruption had not yet occurred. Homo sapiens had not yet reached the Americas. The cave paintings at Lascaux would not be made for another 12,000 years. For 26,000 years, those photons crossed the galaxy, arriving at a planet that, for most of their journey, had no beings capable of understanding what they carried. And in 2022, an array of dishes spanning a planet, built by those beings in the last century, caught those photons, aligned them with atomic clocks, correlated them across thousands of kilometers of ocean and continent, and turned them into an image.
We had the image. We had the measurement. We had the confirmation, more than a century in the making. What we did not have, and still do not have, is any understanding of what lies on the other side of what we photographed. Sagittarius A star is not distant in the sense that matters. It is not abstract. It is the gravitational center around which every star in the Milky Way orbits, including our Sun, including Earth, including you, right now. The carbon atoms in your body were forged inside stars that orbited this black hole. The gravitational influence of Sagittarius A star has shaped the motion of every gas cloud in the galaxy, determined which regions of the galaxy underwent star formation, structured the environment in which our solar system formed 4.5 billion years ago. Your existence, the existence of every living thing on this planet, was made possible, in part, by the gravitational field of an object you can now see in a photograph.
And we still do not know what happens inside. We do not know whether the singularity is real, whether at the center of a black hole there is genuinely a point of infinite density, or whether some future theory of quantum gravity will replace the singularity with something finite and describable. We do not know whether information is destroyed or preserved. We do not know what lies beyond the event horizon in any sense that is accessible to physics as we currently practice it. General relativity says, beyond this radius, my equations break down. The singularity is where the theory confesses its own incompleteness. Every other time a physical theory encountered an infinity, it was a sign that something new was needed. Newton's mechanics gave way to relativity. Classical electrodynamics infinities were resolved by quantum electrodynamics. The singularity at the center of a black hole is almost certainly telling us that general relativity must be replaced by something more complete, a theory that incorporates both gravity and quantum mechanics. We photographed the edge of knowledge. The event horizon is precisely that, a horizon of what can be known within our current framework. Beyond it, physics as we know it becomes silent.
And yet, we pointed a planet-sized telescope at it, and we took the picture. From an animal that learned to write 5,000 years ago, from a species that existed for less than 1,000,000 years, on a planet that has been orbiting a star that has been orbiting a black hole for 4.5 billion years. We photographed the edge of knowledge, and it was beautiful.